Okay, so we're going to go ahead and start. I'm going to try to somewhat quickly go through how to do all this so that you can do all of the homework, and so that during class we can actually, I can actually give you the help that you need instead of having to try to teach you, because that doesn't really seem to be in our best interest right now. So here's how this works. This is all based on powers of 10. Everything for scientific notation is based on powers of 10. So let's make sure we understand how that works to start with. So first of all, we have to remember our exponent rules and what these actually mean. That's the most important part. So what does 10 to the 0 power mean? It means 10 times itself 0 times. So we define that as 1. Okay, anything to the 0 power is 1. 10 to the first power, well, that's literally 10 times itself 1 time, so that would just be 10. 10 to the second power is 10 times 10, so that would be 100. 10 to the third power is the same thing as 10 times 10 times 10, so that would be 1,000. And if you are quick, then you're noticing that the exponent tells you how many zeros you're going to have. So instead of writing out 10 times 10 times 10 for the rest of these, I'll just go by the exponent. So 10 to the fourth power then must be 10,000. 10 to the fifth power must be 100,000. 10 to the sixth power must be 1 million, and 10 to the seventh power must be 10 million. Like that. Okay, which should be what you're pretty used to. Okay, and by the way, this is where our decimal system comes from. It's all based on powers of 10. The ones place, tens place, hundreds place. So that's where that all comes from. On the other hand, when we talk about small numbers and tiny numbers, instead of having a positive exponent, we have negative exponents. So negative exponents don't have anything to do with positive or negative numbers. It just talks about, or it just means that the number is very small. It's very tiny. Okay, so the bigger the negative exponent gets, the tinier the number is. And you'll see that in just a second. Okay, so again, 10 to the 0 power, anything to the 0 power is just 1. Okay, now let's see if we can define what 10 to the negative 1 means. If we remember in our exponent rules, the negative number just flipped it to the bottom of the fraction. So instead of being 10, this is the same thing as 1/10 or 1 over 10. So what does that look like in a decimal? Well, that's the same thing as 0.1, 1/10. And that's where our decimal system comes from. Like, that's how we have determined what each place value is. Okay, so then if we go by definition, the next one should be 1 over 10 to the negative 2. So 1 over 10 squared. 10 squared up here is 100. So that would be 10 times 10. 1 over 10 times 10 is 1/100th. Is 1/100th. And we represent that on the decimal as 0.01. Right? So then the next one will be 1 over 10 times 10 times 10, which is 1 over 1,000. And we represent that as 0.001, 1,000th. So from now on, let's see if we can just keep going by the exponent. So 10 to the fourth power, that should be 0.00001. Okay, so notice here the exponent doesn't tell us how many zeros, but it does tell us how many digits we should have total. So we've got 4, so we should have a total of 4 digits down there. Okay, so 10 to the negative 5th should be the same thing as 1 over 10 to the positive 5, and the positive 5 is 100,000, so that means that this is the 100,000ths place. So 0.00001. Okay, and then 10 to the negative 6 would be 0.000001. And finally, 10 to the negative 7th would be 0.0000001. Okay, so notice the bigger the negative exponent, okay, the tinier the number. So like these numbers are getting closer and closer to 0, right? So this is a 10th, and down here this is a 10 millionth, and a 10 millionth is a very, very tiny, tiny number, and it's very close to 0. Okay, so the bigger the negative exponent, the tinier the number is. And then the bigger the positive exponent, the bigger the number is. Okay, so you need to keep that in mind down here when we start the scientific notation. Okay, so on the next part, we're going to skip down here to the scientific notation part. Okay, so let's talk about, I sort of told you guys this today, but let's make sure we know what all the terms are. So scientific notation is a shorthand way of writing really big or really small numbers. Scientific notation is written as a product. Remember, a product is the answer to a multiplication problem. The product of two numbers. The first number must be between 1 and 10, okay? When we say between 1 and 10, it is allowed to be 1, but it's not allowed to be 10, which means that it can be 1, and it can be 9.999 ... but it can't actually be 10. Okay, so really it's 1 through 9.9999999, etc. Okay, so that's what we mean by it can be 1, but it can't actually be 10. All right, and then the second number must be a power or exponent of 10. Okay, so here's the actual rules that we have to go by. We have to create, notice the verb here, we're going to create a number between 1 and 10 by moving the decimal. Okay, we are going to actually make this number. We're going to force it to be between 1 and 10. All right, and then the next verb, we're going to count the number of times that we move the decimal, and that will be our power of 10, or our exponent. Okay, so to get the number in front, we move the decimal to get a number between 1 and 10, and to get the exponent, we count how many times we move the decimal. Now here's the important part. If your number is greater than 1, which means that, well, if the number is bigger than 1, so 1, 2, 100 million, 45,000, the exponent will be positive. We will have a positive exponent if your number is bigger than 1. If your number is less than 1, which means it is a decimal that starts with 0, so like 0.001 is an example of a number less than 1, okay? This has to be 0 in order for it to be less than 1. All right, and if we have a number like this, the exponent will be negative. And that should make sense to you, because up here, when we had negative exponents, that meant we had a really, really tiny decimal. And when we had a positive exponent, that meant we had a really, really big number. Okay, so negative exponent is between 0 and 1, positive exponent greater than 1, the original number. Okay, So let's actually do some of these problems. So I gave us a little cheat sheet down here to remind us what needs to go where, because they all look the same. All these problems look the same. So first of all, let's create our number between 1 and 10. So this is a whole number, 1,850,000. So that means that the decimal is sitting here. Okay, now we need to move this decimal so that we can create a number between 1 and 10. So let's just think about where we move the decimal. Let's see, if we move the decimal from here to here, how is that going to change our number? Well, that changes the number to 185,000. So basically, it knocks it down a peg. Okay? Moving the decimal place is really the same thing, or the same thing as multiplying by a power of 10. So I'm going to have to continue to move it, because obviously 185,000 is bigger, is not a number between 1 and 10. So let's move it again and see what we come up with. So if I move it again to this place, then I will have 185,000. So now I'll have 18,500. So we're getting smaller, but it's still not small enough. So let's move it one more time. And that gets us to 1,850. So we're getting smaller, but not small enough. We're still don't have a number between 1 and 10. So now I move it one more time, and I've got the number 185. We're definitely getting closer now. Let's move it one more time and see what happens. So now it's between the 8 and the 5. That gives us the number 18.5. So we're getting very, very close, but we're still not there yet. 18 is not between 1 and 10. So let's move it one more time. Let's move it between the 1 and the 8. If I move it between the 1 and the 8, then I will have 1.85. Is 1.85 between 1 and 10? Yes, it is. So that means our mantissa, or the number that's in front of the times 10, is 1.85. Okay? So notice that we're just moving the decimal to create our number between 1 and 10. Okay? All the scientific notation problems will always have a number. The mantissa will always be between 1 and 10. We're creating that to happen. We're forcing it to happen. Okay? So now that we've done that, we can deal with our exponent. So the rules up here say count the number of times you move the decimal point. Okay? So let's just count how many times we had to move it. We had to move it once, twice, 3 times, 4 times, 5 times, 6 times. We had to move it 6 total times. So that means our exponent should be 6. Now we need to decide if it's going to be a positive 6 or a negative 6. It is going to be positive if our original number, and I'm going to erase this so we can see our original number. Remember, our original number was 1,850,000. So we need to ask ourselves, it's going to be positive if it is bigger than, if the original number is bigger than 1. Is 1,850,000 bigger than 1? Yes. So that means that our exponent is going to be positive. So what is our final answer? Our final answer is 1.85 times 10 to the positive 6 power. So that's what your final answer should be. Okay, let's do one more example. So, same thing here. We're going to follow the same steps. Now we've got the number 42,000. So already off the bat, you should be able to tell if your exponent's going to be positive or negative, but we'll save that for a minute. So again, this is 42,000, so it's a whole number. which means your decimal point should be here. If your decimal point is there, and we are trying to create a number between 1 and 10, where do you think we should move it? What if I move it here? That'll give me, that'll just give me 42. Is 42 between 1 and 10? Nope, so I didn't move it far enough. So what about here, between the 4 and the 2? What does that give me? That gives me 4.2. Is 4.2 between 1 and 10? Yes, it is. So I think we've found our mantissa. Our mantissa is 4.2. So notice also that I'm not writing 4.2000. You don't have to write the trailing zeros. Okay, so we call these on the back here, we call those trailing zeros. You don't have to write those, okay? You just need to write the 4.2 because that's the whole point here. The whole point is to shorten it. Well, it's the zeros that are in our way anyway. So why don't we shorten those a little bit or not write those and make use of the power of 10, because the power of 10 is just going to be adding zeros here. That's the whole point of this, okay? Now, we moved our decimal place enough times to get the number 4.2, so now we need to decide about our exponent. So we moved our decimal place from here to here, so how many times is that? 1, 2, 3, 4. That's a total of 4 times, so our exponent should be 4. Now, is that going to be a positive 4 or a negative 4? Well, our original number was 42,000. Is 42,000 bigger than 1? Yes, it is. So we should have a positive exponent. So our final answer for this problem should be 4.2 times 10 raised to the 4th power. Okay? All right, so one way, well, I'll show you that in a minute. Okay, so that is what happens if we start with a big number. So a number that's bigger than 1. So what about if we have numbers that are smaller than 1, numbers that are between 0 and 1, like this one. So I know that it is between 0 and 1 because this number here is a 0. If it was a 1 here and we had a bunch of decimals, then it would not be between 0 and 1. It would be bigger than 1. Okay, so because this front number is a 0, I know that this is a number that is between 0 and 1. Okay, so the process stays the same, really. We're still trying to make our mantissa between 1 and 10. So we've got to move this decimal so that we end up with a number between 1 and 10. Okay, so let's see what happens here. If I just move it this one time, how does that change my number? Well, that'll just make us have 0.07826. So all that did was chop off one of the leading zeros. Okay, and remember we don't really need to mess with those, so we can always kind of skip over those. So we know it's going to be at least after the leading zeros. So let's put it here, and let's see what number that gives. So we're just going to use this part of the number, and that's going to be 7.826. Is 7.826 between 1 and 10? Yes, it is. So that's what our mantissa is going to be, 7.826. I don't have to write these numbers, our leading zeros, just the important numbers, the non-zero numbers. Okay, so that was our mantissa. So now let's go back and let's look how many times we had to move the decimal. So we had to move it, we started here and ended here, so we had to move it 1, 2, 3 times. We moved it 3 times, so that means our exponent should be 3. Now we need to think, is it going to be a positive 3 or a negative 3? Well, our original number, remember, was 0.007826. So this number here is 0, which means that it is somewhere between 1 and 0. Okay, so it is a small number. So if we have a number that is between 1 and 0, or 0 and 1, then our exponent will be negative. So our final answer here should be 7.826 times 10 to the negative 3 power. If you do not put the sign, then you will probably have the wrong problem. Because if you, well, I'll show you the difference in our calculator. Let's go type this in our calculator, and let's put the negative exponent in there, and then let's not and make it positive and see what happens. So 7.826. Okay, so I've got here on my calculator 7.826. Oops, I didn't type it all. 7.826, and then times 10, and then remember our caret button gives us our exponent, so we said to the negative 3rd power, and let's see what that gives us. Okay, so that gets us back to our original number, so that's good. That means we did it right. Let's see what happens if we have the exponent positive. 7.826 times 10 raised to the 3rd power. Ooh, and that gives us this number, which is obviously bigger than 1. So this number is bigger than 1. This number is smaller than 1. All right, so that's the difference between your positive and negative exponents. This was the, this one here was the answer that we wanted, okay, because that's what we were converting to scientific notation. So if you do not put the negative there, then you'll get the wrong answer. Okay, and that's also a way that you can check it in your calculator, by the way. If you want to make sure you've got the right answer, then you can type it in your calculator, and well, as long as the number's not too big, it will give you the answer here. Okay, so let's do one more practice problem. All right, so this one says convert the number to scientific notation. So, same process again. Let's start with our decimal. We're going to move it so that we have a number between 1 and 10. Remember, it is allowed to be 1, but it cannot be 10. Okay? That's what this less than or equal versus just the less than symbol there. Okay, so let's move it here after the 1, because these would be all the leading zeros, right? So really, that would just get us to the number 1. Is 1 between 0 and 10? Well, no, but is our mantissa allowed to be 1? Yes, it is. So 1 is our mantissa, okay? And now we need to find our exponent. So our exponent is how many times we moved the 0. That was 1, 2, 3, 4, 5 times we had to move it. So our exponent is 5. Is our original number bigger than 1, or is it between 0 and 1? Well, it looks like a really tiny number here, so our exponent should be negative. It should be between 0 and 1. So our final answer should be 1 times, oops, I said I wouldn't do that. 1 times 10 to the negative 5 power. All right, and there is your final answer there. So that's pretty much how to actually put a number into scientific notation. Let's look real quick, though, at how to order these, how to make sure that we know which one's bigger than the other one. Okay, let's just use the ones that are here, and we're going to order them from least to greatest here. So let's just take our original numbers here. I'll take this one, and I will take this one, and then I'll take, whoops, and then I'll take, oh, come on. Then I'll take this one. And finally, I will take this one. Okay, and I'm actually going to add a couple just to throw a wrench in here. So let's also add 2.3 times 10 to the 4, and then let's also add 5. No, let's change that. Let's add. I'm thinking. Let's add 1.2 times 10 to the negative 5. Okay? Now, here's the key in deciding if a number written in scientific notation is bigger or smaller. So luckily it's actually pretty quick. You just need to look first at the exponent. Okay? So if you have an exponent that is positive, obviously the more positive, the bigger the number. The more negative, the smaller the number. So just looking at the exponents, you should be able to put them in correct order. So what is the smallest number here? Well, the smallest number here would be the one with the smallest exponents. Well, we've got two of those here. We've got this 1.10 to the negative 5, and we've also got 1.2 to the negative 5. So I know those are going to be our two smallest ones. And then up from there, negative 3 is a little bit bigger. And then from there, we've got two 4s, so they would go together. All right, and then finally we would have our 6. Okay, so our 6 is the biggest exponent, negative 5 is the smallest. So I'm on a good start here, but now I've got to decide about the ones that have the same exponent. When they have the same exponent, then you have to do a little more digging. You need to look at the mantissa too. Okay, so we've got two of them that have the same exponent. All right, let's start here with the least ones, with the smaller ones. Well, let's just look at the mantissa. Which one is bigger? Is 1 bigger or is 1.2 bigger? Well, pretend like this 1, that's the same thing as $1, and the one over here is like $1.20, right? So definitely this one would be bigger. 1.2 would be bigger. So are they already in the right order? That one's smaller than that one. Yes. Okay, so we're good there. All right, so let's see if we need to make a change for the other one. Okay, so over here we've got 2.3 and we've got 4.2. So which is bigger, 4.2 or 2.3? Well, obviously 4.2 is bigger than 2.3, and it looks like they're already in the right order. So we didn't have to change anything. All right, but that's in general how you do it if the mantissa happens to be what you need to look at. Okay, so first look at the exponents and then look at the mantissas for ones that have the same exponent. Okay, so that's going to take care of putting numbers into scientific notation, and that should let you at least get started on stuff so that we can use class time more as getting help on different ones. Okay, see you guys.